So, hello everyone. I would like to start this presentation, present the members of our team. So here we have the professor, José Alberto and Marcelo Rovai. As our Scrum Master, we have Rodrigo Moreni, and the students, my dear friend Ghuilherme Silva, and I, Mateus Lima. So, basically, our project is a Atrial Fibrillation and a Sinus rhythm detector, using machine learning applied in embedded systems. And before we get into the details, we would like to do a disclaimer saying that this project doesn't have the intention to substitute any medical diagnosis, and here we just want to show the capabilities of this new technology and how it can help us. So, starting the presentation, we get some information to show you how much of a problem AFIB is. So, the first one is the estimation worldwide is that AFIB's occurrence is in the range of 0.4 to 1% of the world population. The second, we have the AFIB can increase by 5 to 8 times the risk of a patient developing a stroke. And the last point is that AFIB is responsible for 33% of all arrhythmias emergency admissions. So with only these 3 points, it is very obvious how much of a problem this arrhythmia is for the care system around the world. And now, maybe we are thinking how TinyML can help us. And well, this technology can provide us the capability to achieve solutions with a low price, a good portability, great configurability, and capable of giving us a quick inference about the problem. So knowing a little bit more about the problem and the technology that we are going to use, we arrive at the question, what is the solution? So we are trying to develop an expensive product capable to accelerate the diagnosis and help to detect AFib and prevent bigger problems. So we are going to use a heart sensor to help us to capture the single lead signal from the heart and use some public datasets with an extensive variety of data to have a good generalization and then train the model. Here we have the steps that we are going to open in this presentation and talk a little bit more of each one and show you what we did. And basically we have the raw data sets and we have to select the data that we want from them. And then we have to do some DSP, some digital signal processing steps where we are going to treat this data. And after we have to think about the feature engineer and how we are going to fit or enter with this data into the model. After that, we have the steps of training the model, do the tests, and convert and shrink this model so we can fit it to a microcontroller. And talking a little bit more about the 4 first steps that we have, we need to keep in mind that everything we do in a high level with Python, in these 4 first steps, we need to replicate in a low level using C or C++, so it can work in a microcontroller. So after that, we are now going to understand how the signals of the heart are composed. So here we have the 4 principal frequencies that compose our signal. The heart frequency between 0.67 Hz to 5 Hz, the P wave between 0.67 to 5 Hz, the key area segment between 10 to 50 Hz, and the T wave between 1 to 7 Hz. After that, we have to understand the principal noises presenting our signal, and the first one is caused by musical movement between 5 to 50 Hz, other one caused by breathing between 0.12 to 0.5 Hz, and the last one caused by electric line interference between 50 to 60 Hz. Here we have some information about our dataset, and we are using the German dataset, and here we get some info. So we have the SR that represents almost 77% of the data presented in the dataset, with an average age between 58 years, and a balance between men and women of almost 50-50 for each one. After, we have the AFIB that represents almost 7% of the data, with an average age between 70 years, and a balance between men and women of almost 50-50 as well. And we also have some info about other arrhythmias here. So, to work with these data sets, we only select these 2 signals as a tell with on lead, and after we do some DSP steps, taking account those frequencies that I showed before. So we use a Butterworth of second order as a high pass filter with a cutoff frequency of 0.5 Hz, and a Butterworth of 50 order as a low pass filter with a cutoff frequency of 40 Hz. And here we can see the filters applying the signal, and here we have the raw signal, and here in the bottom we have the filter signal.
Now that Mateus has explained about how filters act on the input signal, it is possible to move on to the next step of feature engineering, which consists of dividing each record of 10 seconds that exists in the database into signals that represent a heartbeat, which is characterized by a 1D image. This procedure aims to make the model able to extract the most important characteristics of each class, where, give the example of the AFIB, it's the irregularity of the peaks and the lack of certain waves. After generating the heartbeats and doing also the normalization, it's possible to build the machine learning model, which is shown in this slide. The most important point in it is the use of 1D convolutional layers, which are indicated for the application of training with images, as they are able to extract the most important features of each image, while simplifying in its terms of size, making with that you have an effective model both in terms of accuracy and memory usage, which is very important in a TinyML application. Here you can view the model training results on the Edge Impulse platform. It's possible to see that the accuracy results of both classes are great, above the 90%, as much the AFIB, SR, and the F1 score. The latency is quite small, only 10 milliseconds, which practically characterizes a real-time classification. We also managed to get a relatively small memory cost for the Arduino we are using, which is the Nano 33 BLA Sense. This slide shows the day we went to our university to use the simulator that is capable of generating different heartbeats in many situations. Sampling was done by a cardiac module together with an ADC module. We used the data collected in it to verify the model's efficiency when operating with records outside the German dataset, and the results were pretty great. Here you can see in the Edge Impulse test section that the model was able to predict the AFIB with 100% certainty for a signal captured in the simulator that was in fact AFIB. This slide shows the same case only for SR, where the model is also right, with a certainty of 89%. Since it was possible to see that the model was already working very well, we moved on to the next step of converting it to use in the Arduino. Once this was done, we tested its quality by placing an AFIB signal on its input, and was observed that the model was able to make the correct prediction with certainty. We tested this method with more signals and the results were the same. In this way, it was possible to check that the model developed and tested in Python on the computer was able to operate in a similar way in a completely different environment with words data, reaching results over 90% of accuracy. Now, just to finish the presentation, we also plan to transform the project prototype into a specialized board that's capable of performing both the measurements of the cardiac signal and the eventual classification of this signal. A preview of this board is shown on this slide. Well, I would like to thank you, all the listeners. Thank you very much, and see you later.